Yeah, so what I want to do is try to tell you about some other important theorems which are connected with normal families. Okay, so the theorem that we are going to look at today is called Royden's theorem. Okay, and the whole point about the theorem is that whether you can decide the normality of a family if you have a growth condition on the derivatives of the functions in the family. Okay, so remember that normality is connected with the derivatives. Okay, Montel's theorem will tell you that if for a family of analytic functions, normality is the same as saying that the original functions are themselves normally uniformly bounded. Okay, and the first the Cauchy integral formula will then tell you that the derivatives will also be normally uniformly bounded, and the normal uniform boundedness of the derivatives will give rise to equicontinuity. Okay, and then you are in an Arzela-Ascoli kind of situation and you will get normal sequential compactness. Okay, and then the same kind of thing, there is the same kind of philosophy with Marty with Marty's theorem as well, because in that case you are looking at meromorphic functions, and then the theorem says that the normality of a family of meromorphic functions is directly the same as the normal boundedness of the spherical derivatives. Okay, so you have to take derivatives with respect to the spherical metric. All right, and then but mind you, normally whenever you have a family of functions that whose derivatives for example, if you have a family of functions which satisfy a Lipschitz condition, okay, that is the difference in the function values are bounded by a constant times the difference in the variable values. Okay, this is the kind of condition that you will get if for example the derivatives are bounded. Okay, so basically if you have a Lipschitz type condition, which is how you must think of a condition where your derivatives are bounded, whenever you have a Lipschitz type condition, then you are actually getting equicontinuity, and then you can apply Arzela-Ascoli theorem to get normal sequential compactness. Okay, so so here is what we are going to look at today is Royden's theorem, which says that if you have a family of functions, okay, and assume that the derivatives of the family, so I'm looking at either I can look at analytic functions or I can look at meromorphic functions. The only thing is that if I look at analytic functions, I mean I must consider the derivatives where they defined. Okay, so if they are meromorphic functions, I should not worry about the derivatives at the poles, and I'm not in principle I'm not looking at the spherical derivatives. Okay, I'm looking at the ordinary derivatives at all points other than poles. Okay, so if the derivatives grow as at most like an increasing function of the original functions, okay, then the family is normal. This is Royden's theorem. Okay, so let me write this down. So Royden's theorem suppose script f is a family of analytic functions on a domain D, the complex plane, such that there exists a strictly increasing function so this is the function psi from non-negative real numbers to non-negative real numbers. So it's a strictly increasing function such that the modulus of the derivatives of the functions in the family, they are bounded by psi of the modulus of the functions. Okay, so this is the this is the condition in Royden's theorem. The condition is that the derivatives of your the functions in your family, the way they grow is at most like an increasing function of the growth of the original functions. So what is there on the right side is psi of mod f, okay. Mod f indicates the growth of f, okay, in modulus, and psi of mod f is psi of the growth of it says that the psi of mod f will be an increasing function of mod f because psi is an increasing function, okay. So what you are saying is that the derivatives grow as an increasing function of the original functions, okay. Then the family f is normal, okay, and the significance of this is that because of Montel's theorem, this will tell you that the family is going to be normally uniformly bounded, okay. It also tells you that the derivatives will also be normally uniformly bounded, okay. It's a very powerful condition, alright. The point is that when you look at this condition, it looks as if the derivatives are growing pretty fast, okay. It looks as if the derivatives are growing. See, what you want is the derivatives to be bounded on compact subsets, okay. You want derivatives to be normally uniformly bounded. That means you want them to be uniformly bounded on compact subsets, which means that on a compact subset you want a uniform bound, okay. You don't but the point is that what this says is that derivatives are growing, but the growth is at most like an increasing function of the modulus of the original functions, okay. So it looks directly doesn't look as if this is going to lead to normality, but the theorem is that it does lead to normality, and the reason is that this is also a kind of boundedness of derivatives with respect to a different kind of metric on the Riemann sphere, which can be defined using psi. So that is the whole idea, okay. So let me write this, let me write the proof. So here is the proof, probably I will use proof. Firstly, assume that psi of t is less than or equal to 1 plus t squared by 2, okay. Suppose you assume this, alright, because I want to then consider the case when it is greater than or equal to 1 plus t squared by 2. Suppose I assume this, alright. Then you see, if you calculate the spherical derivative of any function in the family, what I will get is f hash of z is what? It is going to be by definition 2 times mod f dash of z divided by 1 plus mod f of z the whole square. This is what it is, alright. This is spherical derivative. Mind you, these are all analytic functions, but I can also consider them as meromorphic functions, and spherical derivatives are defined, okay, even for meromorphic functions. So now you see the condition is that mod f dash is supposed to be less than or equal to psi of mod f, okay. This is the condition in the theorem. So I can write this is less than or equal to 2 psi of mod f divided by 1 plus mod f the whole squared, alright. But then 2 psi of mod f by 1 plus mod f the whole squared is less than or equal to 1, that is because of this, okay. So if I assume psi of t is less than or equal to 1 plus t squared by 2, then all the spherical derivatives are bounded on the whole domain, and of course if the spherical derivatives are bounded on the whole domain, then Marty's theorem tells you that this is equivalent to the normality of the family, okay. So this is equal to normality of the family considered as a family of meromorphic functions, but that is also the same as the normality of the family considered as a family of analytic functions. The only thing is that you should allow the possibility that you can have normal convergence to the function which is identically infinity, okay, when you consider the spherical metric, okay. So the case when psi of t is less than or equal to 1 plus t squared by 2 is trivial, alright. It's just because of Marty's theorem. Then by Marty's theorem So let me write this down. F is normal. Okay. So assume the other possibility that psi of t is greater than or equal to 1 plus t squared by 2 for beyond a certain stage t greater than or equal to t naught. Okay. I can replace the function psi of t by another function for which the same condition holds with t greater than or equal to 0. That means I am saying that I can, without loss of generality, I can assume t naught equal to 0. And why is that so? Because you just have to put psi 1 of t to be equal to psi of t plus t naught. If you do this, all right, then you know psi of t plus t naught is certainly going to be equal to is going to be greater than or equal to 1 plus t naught the whole squared by 2, that is if t is greater than or equal to 0. Okay. So the mind you psi of t is greater than or equal to 1 plus t squared by 2 provided the t is greater than t naught. So I need t plus t naught greater than t naught, and that is the same as t greater than or equal to 0. Okay, so I will get this, but then of course this is greater than or equal to 1 plus t squared by 2. Okay, and you know if psi of t is greater than or equal to 1 plus t squared by 2 for t greater than or equal to t naught, I can replace psi of t by psi 1 of t with psi 1 of t greater than or equal to 1 plus t squared by 2 for all t greater than or equal to 0. Okay, and the point is that psi 1 of t is certainly greater than psi of t, because psi 1 of t is psi of t plus something and psi is increasing. So psi 1 of t will be also greater than or equal to psi of t. This will also be true. Okay, and the point is that this is of course because psi is increasing. Okay, and therefore what will happen is that you would have got mod f dash is going to be less than or equal to psi of t, which is less than or equal to psi 1 of t. Okay, so all these considerations tell you that without loss of generality you can assume psi of t to be greater than or equal to 1 plus t squared by 2 for t greater than or equal to 0. Okay, so without loss of generality we may assume that that psi of t is greater than or equal to 1 plus t squared by 2 for t greater than or equal to 0. Okay, you can do that. Now namely if not you replace psi by psi 1, all right, and call psi 1 as psi if you want, all right, again. So and then the next reduction I am going to make is that I am going to assume that psi is also continuously differentiable function of t. That is because you know psi is a monotonic function, okay, and I can always approximate it by a continuously differentiable function. Okay, so we can also assume that psi dash of t exists and is continuous. This is the same as saying psi is C1. Okay, it is a continuously differentiable function. You can do that because after all you can replace psi by any bigger function, okay, and you can replace psi by a bigger function which is smooth. Okay, you can always do that. And well, now you know what one is going to do. One is going to use this psi to give a metric on the Riemann sphere, okay, and look at the induced metric on the domain in the complex plane. So what you do is for z1 comma z2 in the domain, okay, define d psi of z1 comma z2 to be equal to, okay, you see you take integral from z1 to z2 okay, along any smooth path, or along any even piecewise smooth path, even a contour, okay. And what you integrate is that, so this is the you integrate mod d zeta by psi of mod zeta, okay. See, notice, and of course, you know, you have to take the infimum of all this. So this integral is over gamma, so infimum over all gamma, where gamma is a smooth or piecewise smooth path from Z1 to Z2. You take all possible paths, contours from Z1 to Z2, integrate along that this quantity mod d zeta by psi of mod zeta. You do this, okay, and notice that, you know, the point is psi is, see, try to understand, psi is greater than, psi of t is greater than 1 plus t squared by 2. So 1 by psi will be bounded by 2 by 1 plus t squared. 1 by psi of t will be less than or equal to 2 by 1 plus t squared, okay, and 2 by 1 plus t squared is you know, that is the form of the integrand that you will have to put when you want the spherical metric, okay, and 2 by 1 plus t squared is bounded as t goes to infinity if you want, right. So it's the integral is always nicely defined, all right. So you take this infimum, all right. Then the point is that this gives you a metric on the this d sub psi, the way I have written it, it gives a metric on the Riemann sphere, okay, or you can think of it also as a metric on d, d considered as d identified with its image in the Riemann sphere if you want, okay. But the point is that this gives a metric, okay, and you know, in particular an infimum of a set of quantities is always you know, less than or equal to each of those quantities. So if for gamma I had taken the straight line path from Z1 to Z2, this is also less than or equal to integral from Z1 to Z2, okay, straight line path, straight line segment from Z1 to Z2 of this quantity mod d zeta by psi of mod zeta, okay. And the point is that see, but the point is that this is bounded, see, 1 by psi zeta is bounded by 2 by 1 plus mod zeta the whole squared, because that is exactly that is this condition, right. We have assumed psi of t is greater than or equal to 1 plus t squared by 2, okay. So 1 by psi of zeta, psi of mod zeta is going to be this is going to be bounded by 2 by 1 plus mod zeta the whole squared, okay. You have this, alright. So this is bounded by integral from Z1 to Z2 mod d zeta 2 mod d zeta by 1 plus mod zeta the whole squared, okay. But what is this? This is actually the spherical length from Z1 to Z2. So this is just d spherical of Z1 comma Z2. So what you have proved is that the d sub psi is a metric which is bounded above by the spherical metric, okay. But the point is that for this for the spherical metric, the Riemann sphere itself is compact, okay. It's compact with respect to the spherical metric, because you know the spherical distance, the maximum spherical distance is there is a maximum to it. It is you know, it is going to be just the half the circumference of a sphere of radius 1, okay. It is going to be namely it is going to be just pi. That is the maximum distance you can get on the Riemann sphere. The Riemann sphere is a sphere of radius 1, okay. Then any great circle on it will have radius 2 pi, I mean will have circumference 2 pi, okay. And the maximum distance you can get is from the, for example, from a point to its antipodal point, for example from the north pole to the south pole, north pole representing infinity, south pole representing 0, and the maximum distance you can get is pi. So see, it's a space with finite diameter, and it's compact, okay. And the point is that for a compact space, okay, if one metric is bounded above by another metric, then these two metrics are uniformly equivalent, okay. So the point is that since the Riemann sphere the Riemann sphere sphere, or you can just consider C union infinity or the extended complex plane is compact with respect to the spherical metric, okay, we have that these two metrics d psi and ds are strongly equivalent. So at this point let me very quickly tell you about this strong equivalence. See, if you have two metrics on a space, we generally say that these two metrics are equivalent if they induce the same topology, okay. This is called weak equivalence, okay. Now what is strong equivalence? A strong equivalence is a condition that each metric is bounded by the other metric by up to a constant, an absolute constant. So if you have two metrics d1 and d2 on a space X, to say that d1 and d2 are equivalent for X means to say that the topology induced by d1 is the same as topology induced by d2, okay. One of the sufficient conditions is that every ball in d1 contains a ball in d2 and every ball in d2 contains a ball in d1, okay, the nesting of balls condition as it is called, okay. So this is just to say that the two metrics are topologically equivalent, but there is something called strong equivalence. Strong equivalence is that the two metrics, each metric is bounded above by the other metric up to multiplication by an absolute constant. So if the two metrics are d1 and d2, you should get d1 less than or equal to lambda d2 and you should get d2 less than or equal to mu d1. You should be able to find such absolute constants. If you are able to find such absolute constants, these metrics are said to be strongly equivalent. Now of course strongly equivalent means equivalent, but what is the beauty about the strong equivalence? It is the following. See, if you on a space, suppose you are considering functions, continuous functions, okay, then if you change the metric to an equivalent metric, that is you change it up to weak equivalence, okay, that is you change the metric by another metric which gives the same topology, continuity will not be affected, because after all you have not changed the topology, continuity just depends on the topology. But the problem is uniform continuity will become a problem, okay. If you have a uniformly continuous function, okay, on a subset, suppose you have a function which is continuous, which is uniformly continuous on a subset with respect to one metric. If you replace that metric by an equivalent metric, the uniform continuity may not be preserved. If you want also the uniform continuity to be preserved, you should replace the metric necessarily by a strongly equivalent metric, not just by any other metric which will give the same topology. So what will happen is that if you change the metric by just another equivalent metric, namely you don't that you are only worried about the topology, what will happen is that a function which is continuous uniformly with respect to one metric may fail to be uniformly continuous with respect to the other metric. But if you want to preserve uniform continuity, you have to replace the metric only by a strongly equivalent metric, okay. And the point is that you see, if you have two metrics on a space and such that one metric bounds is an upper bound for the other metric, and the bounding metric with respect to the bounding metric the space is compact, then it also means that the some multiple of the smaller metric, some multiple of the smaller metric also bounds the larger metric. That can be proved, okay, because of compactness. Therefore just the bounding of one metric by another on a compact space where the bigger metric, where the space is compact with respect to the bigger metric, will tell you that they are strongly equivalent, okay. Now you know why I am saying all this. I am just saying all this to tell you that, you know, if you are looking at a family of functions, you know, to decide uniform continuity with respect to the spherical metric, I can as well decide uniform continuity with respect to the metric, any metric that is strongly equal to the spherical metric, okay. And so this applies to uniform continuity, it applies to equicontinuity and things like that, right. So we are now more or less done. See, now what you do is that now you look at the following thing. So if you calculate for small f in script f, what happens is that if I calculate the under the new metric d sub psi, if I calculate f z1, f z2, okay, what will I get? This is going to be infimum over all contours from z1 to z2, integral from z1 to z2 along that contour gamma of mod d zeta by psi of mod zeta. This is what it is, with the substitution zeta equal to f of z. Okay, this is the definition, right? And what is this going to give me? See, notice that this is being an infimum, this is certainly less than or equal to the integral over the straight line segment. Okay, so if I take this integral over z1 to z2 and I take the straight line segment, what I am going to get is mod d zeta by psi of mod zeta, and of course I have to put zeta equal to fz. So if I do that, I am going to get integral from z1 to z2 along the straight line segment of, I will get mod f dash of z into mod dz, because that is what mod d zeta will be. Okay, and I will get mod divided by psi of mod fz. Okay, but then what is the hypothesis in the theorem? The hypothesis in Royden's theorem is that the numerator of the integrand mod f dash of z is bounded by psi of mod fz. So it means that this integrand is less than or equal to 1. So what it means is that I will get this is less than or equal to integral from z1 to z2 over the straight line segment of mod dz. But integrating mod dz will give you just Euclidean metric. Okay, so this will be, it will simply be mod z1 minus z2. This is all that I am going to get. Okay, so all right. So what have we proved? We have proved, therefore, that what is there on the left side? On the left side I have d psi of f z1 z1 comma fz. You have proved that this d psi of f z1 f z2 is bounded by mod z1 minus z2. That is a Lipschitz condition. That is a Lipschitz condition on f with respect to the new metric d psi on the Riemann sphere. But the moment you have a Lipschitz condition, it implies equicontinuity. So it means that the family f is equicontinuous. Okay, this family script f is equicontinuous with respect to the metric d psi, but then d psi is strongly equivalent to ds. Therefore the family script f is also equicontinuous with respect to the spherical metric. But if it is equicontinuous with respect to the spherical metric, I can use as in the proof of Marty's theorem, I can use the Arzelà-Ascoli theorem, and I can use a diagonalization argument to conclude that the family is normal, and that is the proof. Okay, so thus script f is equicontinuous on d with respect to the spherical metric, but since the spherical metric, script f is equicontinuous on d with respect to d psi, but since d psi is strongly equivalent to the spherical metric ds, script f is equicontinuous on d with respect to the spherical metric. Now by the Arzelà-Ascoli theorem, and a diagonalization argument, we conclude script f is normal. It's a normal family. Okay, so that's the proof of Royden's theorem. So the whole idea is that this Royden's condition is actually the Royden's condition translates to a Lipschitz condition when you use different metric on the Riemann sphere. Okay. So what is the advantage of this? The advantage of this is we can apply it to an example like this. Let D be a domain and script f be the set of all functions f analytic on D, such that mod f dash of z is bounded by e power mod f z. Look at functions like this. Mod f dash is bounded by e power mod f. Okay. Now then this family is normal, because here e power mod f is the function e power t, and e power t is of course a smooth it's an increasing function of t for t greater than or equal to 0, and you can apply Royden's theorem. Okay. So you get this nice condition that if you are looking at a family of analytic functions whose derivatives grow at most as the grow exponentially as the functions. Okay. The derivatives are f dash, the derivatives of the functions are given by f dash. Okay. And their moduli mod f dash, that is the rate at which f dash grow, and mod f dash is bounded by, is at most like e power mod f, that is a condition. But the function involved is e power t, which is an increasing function of t. Alright. And mind you, this is for any domain. For example, if you are taking the domain to be the whole plane, okay, e power mod f, okay, could e power mod f is a kind of exponential growth. Okay. And it seems to be even if you put mod f dash is equal to e power mod f, okay, it looks like the derivatives are growing exponentially as the original functions. Okay. But so it looks as if the derivatives, it seems as if the derivatives cannot be normally uniformly bounded. It looks, because whenever there is something growing exponentially, you are worried about boundedness. Okay. So if you take a compact subset of the domain, alright, one is worried whether whether the derivatives will be bounded, but the truth is they will be, and it's not obvious, it's not an obvious result. What you have is the derivatives are growing exponentially, okay, as the original functions, and from that trying to conclude that the derivatives are bounded uniformly on any compact subset is a great thing. So you see, Royden's theorem will now apply. It will tell you that this family is normal, but if this family is normal, Montel's theorem will tell you again, or you can directly even use Marty's theorem. Marty's theorem will tell you the spherical derivatives are bounded. Okay. And if you want, you can use Montel's theorem, which will tell you that the original functions are themselves normally uniformly bounded. Okay. So if you take a compact subset of the domain, then the functions are themselves uniformly bounded, and the Cauchy integral formulas will then tell you that the derivatives of the functions are also normally uniformly bounded. They are bounded on every compact subset, which is not at all obvious because the derivatives seem to be growing exponentially as the functions. So that is the significance of this theorem. Okay, and it has got to do with the study of normal families, and that's the reason why I wanted to present it here. Okay, so I'll stop here. So let me complete this sentence. I'll just say that then by Royden's theorem, script f is normal. In particular, the derivatives of f belonging to script f are uniformly bounded on compact subsets of D, which is quite surprising. given that the original condition was just that the derivatives are growing exponentially with respect to the functions.